Our first talk at the conference is Kasra Rafi from Toronto. The title of this talk is Strong Contractibility of Geodesics in Mapping Class Group.
Thank you for the introduction, and it's so good to be here, see so many familiar faces. So yeah, this is going to be a nice, relaxing talk. So the first talk of the conference. Please feel free to heckle and laugh. Yes, that's all. So I'm going to talk about the mapping class group. So we start the like controversial. That's my invitation for the mapping class group. There was a deal made with Juan, so the mapping class group is MAP. So I would like to think about the geometry of the mapping class group. But there is a lot known about the geometry of the mapping class group, so maybe I'll just write it down. So much is known about the geometry of the mapping class group. And the main, most of this can be characterized in the distance formula, right? So the main theorem, I would say, in the field is the distance formula, which says the word length of a mapping class is the sum of distance and subsurface projections. Maybe let's try it like that. Yeah, we can put some more symbols here. Let's put K here. Maybe make the equality be squiggly, and some overall ones. So everybody hopefully has seen this. They know about this. So what is dy? The dy of phi is you pick your mu0 to be a fixed marking, and then you look at the subsurface projection distance between mu0 and phi of mu0. So if you have this is a measure of complexity coming from the subsurface. So mu0 is some fixed marking. So this has lots of consequences. For example, it tells you that the mapping class group is not a hyperbolic space. In the sense of Gromov. You could in fact do this more easily, like if you have a map from a Z2 to the mapping class group, which sends I and j into, let's say, d alpha i, d beta j, and the intersection of alpha and beta is 0. This is a quasi-isometric embedding. In fact, this sentence, I think, follows from the work of Farb and Minsky. They prove that the word length of the gain twist grows linearly. So it's not at all hyperbolic, but it has directions which kind of look like hyperbolic spaces, right? So the curve complexes that are involved in the distance formula are hyperbolic. So as long as you don't have this issue of disjoint subsurfaces, things are hyperbolic, right? So axis of a pseudo-Anosov element is like a hyperbolic direction. These are like all old news, so it's kind of nice to talk about it. There are many versions of this sentence that have been proven. So let me write some names here. So Minsky proved this for the axis of the mapping class group in Teichmüller space. Jason Burstow proved this in his thesis in the sense of asymptotic cone. If you get asymptotic cone, the axis will actually have two different endpoints. The Moon and I proved a version of this, which I might state a bit later. And also there's a version of this for the Hans complex. So there's well, Minsky, which proved that if you look at the axis in the Hans complex, it also like hyperbolic space. So what does this mean in particular when you say it's like hyperbolic space? It could mean many different things. It could mean that it's Morse. Right? If I pick a quasi-geodesic, it stays near the geodesic. Or it could mean that it has the contracting property. So this means that if I pick a large ball and I project it down here, however large the ball is, the projection is bounded. So this is true in H2. So that's why you say this is like a hyperbolic space, because the geodesics in H2 have this property. So let me prove that for you, because it's very quick. So here is H2. Here is a geodesic in H2. That's the easiest geodesic you can take. So here is a ball that is disjoint from H2. Any ball that is disjoint from H2, you can fit it inside of the bigger ball, which the biggest ball you can have is when you touch the infinity, which is over here. You can make this be 1, then I can ignore the smaller ball. Then this Euclidean length is the square root of 2. And if I look at the projection of that, I have to look at two geodesics going like that. So if this radius is 1, that's root 2 plus 1. This is root 2 minus 1. The length of the projection here is at most log of root 2 plus 1 over root 2 minus 1. So any ball in hyperbolic space that is disjoint from a geodesic has a projection where the length of projection is bounded by that number. Okay, so that's very good. So you want to try to prove a sentence like that for the mapping class group, and you wonder if it's true. There are several issues. As I said, the main tool here is that distance formula. And the distance formula doesn't have an equality here. As a little, these lines are not so straight. There's a constant here, right? So this causes a lot of issues. If I write A is strictly equal to B, usually this means there exists maybe little, let's say capital K and capital C, such that A is less than or equal to K times B plus C, and is bigger than or equal to 1 over K times A minus C. Right, so that's what that means. So in particular, not equality. So to get away from this non-equality, so you have to introduce more constants into your statements. So for example, the statement that is true in the mapping class group that we showed is the following thing. So let's say this G is a geodesic in the mapping class group, which is thick, let's say the axis of a pseudo-Anosov. And I have a point X, which is distance R from this axis somehow. First of all, the closest point projection is already a problem. Right? If you cannot discuss the distances, and the distance of defined up to some multiplication, the closest point projection doesn't make any sense, so you don't have any good way of projecting to begin with. And the second thing is, if you pick a ball of radius R here, then you have not so much control of what's really going on. So you have to pick kind of a smaller ball.
Are you you're in the mapping class?
This is the Cayley graph of the mapping class. Yeah. And this is a geodesic in the mapping class group, which is preserved under the pseudo-Anosov. And you pick a point here, so these elements are all mapping classes. That is some distance R from the axis.
Is there an axis in pseudo-Anosov?
Yeah.
And actually on the nose geodesic, which is invariant?
Yeah, there's a point which is there is a unique one, but there's a point which has the smallest translation. You connect it with a segment, and then you push it forward. You get the axis. I mean, there's not a unique axis. I mean,
It's not a geodesic.
it's not a geodesic.
Oh, okay.
That's right. So,
Okay.
or you could pick a geodesic that is quasi-preserved.
Oh, okay, fine.
Oh, okay.
Fine.
So that's also, you can just pick whichever you like.
Okay.
Maybe I pick it because it's quasi.
Okay.
Right? So by axis from now on,
Okay.
if I apply phi to this, it will go somewhere here. Right? If I pick a point y here, phi of y is something.
Like these curly letters, right?
Yeah. Or maybe I'll just draw a T. I mean, I haven't started making actual sentences. This is a this is a schematic picture. It's a schematic picture.
It's a relaxing talk.
So, but it's, yeah, but how it says actually maybe also wrong. First of all, you don't have an axis. Second of all, you don't have closest point projection. You don't know there is a point which is the closest point projection. Yeah. So these are all actual issues.
Okay.
So writing precise sentences like that is kind of tough. So what you do usually is, first of all, instead of picking a ball of radius r, you pick a ball of radius cr, where maybe I should have too many c's, let me call it rho r, where rho is some number bigger than 0 and less than 1. It can give you a tiny number, and then you define the projection somehow differently. You pick it, you look at the projection in the curve complex, so that's kind of easier, right? Because there's a shadow of all this in the curve complex, which also you have a quasi-axis. So maybe I write this down. What is the map from the mapping class group to the curve complex? Well, I sent phi into phi of my mu 0. So I have fixed some marking, which is a bunch of curves. I apply phi to it. I get a bunch of other curves. I choose one of them at random. So I have some kind of a map over here. So I can redraw this picture in the curve complex. And then, so if I pick a point phi in here, it's a phi point, there's a phi of mu 0 here, and then there is a curve alpha, which is the closest point projection. Here, curve complex is actually hyperbolic, so this makes sense up to some IT error. I can bring this back over here, and I find some point over, right? So I call this the projection to G. Right. So the statement is that there exists a C and a B, rho and a B, such that for every G and every R, if I look at the projection to G of ball of radius rho r around X, then the diameter of this is less than or equal to B. So the assumptions are the distance from X to G is R. And G is thick, or maybe it's the axis of a pseudo-Anosov. So under these assumptions, if I pick a point kind of far away and I pick a ball, which is really, really large ball, it's smaller, but definite proportion is smaller than the original ball, the projection is actually going to be bounded. So this is the kind of sentence you can prove, and then this is enough to prove that the axis is Morse, and so you get most of the consequences that you want out of this sentence, so you can kind of stop. Right. So that's the story. So I mean, as it was. But maybe you want to do better. I mean, first of all, you might think that this switching this R to rho times R maybe is just a laziness thing, and then so you didn't really have to do that. If you picked a bigger bar, you could still project it, and it could be bounded distance. But you just didn't want to, because this is enough to do what you want, and then you have no reason for it. But it turns out that there is an application to prove this. So let me say, if this happens, I would say, if every G has this property, I would say G has the contraction property.
Are you raising the issue of the question is whether you could take rho to be 1?
Yeah.
Is that
That's
what you're
the question is, can you actually take rho to be equal to 1?
Okay.
And could actually something go wrong?
Yeah.
Or nothing goes wrong, you just can't prove it. right? And the question is, or can you even compute the distance between any 2 points in the mapping class group precisely? Like ever. So exactly, so can you give me an example of a single geodesic in the mapping class group? Right? So sentences like that. So, and the thing is, you might think that, oh, of course you can if you just put energy into it. Right? So if you really wanted to, you could do it, but just nobody cares. Source geometry is good enough, right? So maybe that's the story. So the question was, is that really a story or not? And in fact, this question, there is a reason for it a little bit more. If you're thinking about the growth tightness, which I don't want to talk about it, there's a distinction between this contracting property and the strong contracting property. If you want to prove the action of the mapping class group on some space is growth tight, you would need actually a stronger sentence.
What's the word?
So growth tight. Growth tight, I'm not going to define, but there's a notion of a growth rate, which has to do with G, the group G, maybe some generating set of the group. And the growth tightness means that if I quotient G by some other group, H, or by some element, which acts loxodromically in an appropriate sense, and I pick the projection of the generating set, then the growth rate goes down for sure. Like every time I take any quotient of G by a loxodromic action, the growth rate actually decreases strictly. Right? So let me not define this, but so anyway, to prove that an action of, so you can do this for action of G on its own K graph or some other group. So there was a theorem by Chris Cashin and Jim Ta. So they proved that the mapping class group's action on the Teichmüller space is growth tight, and they asked the question. So the question was, what about the action of the mapping class group on its own K graph? And it turns out that the important sentence that you would need here is if the axis of pseudo-Anosov in the mapping class group has the strongly contracting property. So what does that mean? It's kind of means
It would answer the question as yes?
That's right. It would answer the question as yes. I mean, Jing is here, so she can correct me if I'm saying something wrong. But yeah, it would answer the question as yes. And the strongly contracting property would mean that if I picked, so there exists a B and C such that if I project to G a ball of radius R minus C, not R times rho, to G, then the diameter of this set is less than or equal to B, again with the assumption that the distance between X and this geodetic G is equal to R. So you would say G has a strongly contracting property if you could actually prove the sentence which is true in H2, like with additive errors instead of with multiplicative errors.
So that's no different than one without the C, because the projection.
That's correct. That's correct. That's correct. I mean, no, that's true. That's true. I mean, so what am I worried about? That's right. The projection has to be Lipschitz. This is no different. Right. I mean, the thing is, I want the ball of radius. Yeah. Maybe you can remove that. But I want the ball to be disjoint. I mean, there's an issue that the ball of radius, even though your distance is. Yeah. What am I worried about? Yeah. Let's remove this C. But this is important to know that it's okay. This is what I'm going to prove, so, which is a little bit easier to prove, right? So you're right. I mean, so that it's actually very important that this C doesn't matter. So when I'm going to put it in, you guys shouldn't care because it doesn't matter. No, I mean you could or could not put it here. I'm going to prove this sentence.
That it is strong.
No, that this sentence is not true. It's stronger. It's stronger. That's true. So, depending on your taste, you can ignore this. Yeah. Okay. Yeah. I mean.
Can I ask a question?
Yeah. Let me erase it.
For the application, do you need every pseudo-Anosov to be strong?
No, you just need to have one. You just have to have one. I mean, it depends what you want to prove for growth practice. Like if you want to find a quotient which has a lower growth, then you just need one. If you want to prove any quotient is, yeah. So every time you have an axis which has this property, then adding this as a relation will reduce the growth strictly.
Are you talking about quotient?
So quotient, it just means you just add that element into the relation and make it the identity.
It's a normal closure.
It's a normal closure.
It's a also just act on the space.
That's right. No, I think it's a clue. But again, you can correct me. But yeah, it's a clue. You just add that to the relation.
Sorry, can I just ask this has been bugging me? So you quantify this over here incorrectly, right? And this statement is not for every G. This is,
Yeah,
G has a contracting property, this is true
if
for
this is
pseudo
true.
G.
Right.
You're not asking that there be uniform constants that work for every pseudo-Anosov.
So this is true that, so what, yeah, you're right. But at the same time, every pseudo-Anosov, there's a uniform constant which works for every pseudo-Anosov. This, I mean, there's no.
The thickness.
That's right. I'm sorry. Not every pseudo-Anosov. What is going to infinity here is R. Right. So the geodesic is fixed. The constant rho and B are
All G
fixed.
should be on the left.
So
Yeah.
let's see for every R. So for well, the G is there for all G doesn't exist. Yeah, let's ignore that. That's right. So G has the kind of property if they're constant, such that for every R. So this is the enemy. The R is the enemy.
Right, but you're not asking for uniformity.
Not uniform. That's right. That's right. Yeah, just one guy. I mean, if you want to get a strictly lower or yeah, you just need some constants to work for somebody. And you get that. Good. Any other questions? Okay, so anyway, so this is the setup, and then you want to try to see if you can prove it, and then it will be kind of weird if you cannot. But so what we do is give an actual comparison. Right? So that's why it's a fun talk, because it's I'm not proving something you might want to prove, you cannot. Right? So and then you do the simplest possible case. So let me just write the theorem. So I can state who it is. Yvon Verberne, she's a graduate student at Toronto. So what we prove is that there exists a generating set. Let's call it S. For the mapping class group of the 5 times punctured sphere. And a bunch of constants. So there is a phi, which is a pseudo-Anosov. And maybe a bunch of other constants, and just write down what I want to, right? So there's a sequence of points, WK, which are elements of the mapping class group, and RK, which are radii going to infinity. Such that the distance of WK and G phi, which is the quasi-axis of the phi in the mapping class group, is bigger than RK, but the closest point projection of ball of radius WK with RK has diameter large. Which is logarithmic which is bigger than equal to log of arc.
So you don't actually use this minus c in your
C.
statement.
Hmm?
So you don't actually need that minus C up there.
The minus C doesn't really matter. I mean, you shouldn't be, the minus C doesn't matter. I mean, I'm going to have a lot of additive error issues near the geodesic. And every time this happens, I'm going to say, don't worry about it. Right? So, so this is just to, to say that ahead of time. That I'm not going to worry about additive errors, but you should be very careful about multiplicative errors. Right? So, yeah. So there exists a C also somewhere. There exists a Leibniz group, a constant C, positive phi, which is also a bunch of points, a bunch of arcanes, which have this one. Okay, so that's it. So I'm going to just spend the whole time doing this one example. And it's kind of a cute example. So hopefully you guys will enjoy it. So let's start slowly. The thing is, if you pick your usual generating set for the mapping class, it's hard to prove anything. It's hard to know that the paths are efficient. It's hard to show something with a geodesic. To show something with a geodesic, you have to have these extreme shortcuts. What you're doing has to be demonstrably efficient. So I just add some generating sets. So certain words are really, really efficiently doable, right? But I want to add a twist to it so I can create this craziness. So
Does this really depend upon the generating set? Like, where does that show up? And like, wouldn't it just change all the constants, or?
everything depends on the generating set. And I say the distance to the geodesic,
Right.
that depends on the generating set.
Right, but it would still do it with vanity, right? If you just change your generating set.
If I change my generating set, the distance of a point to geodesic changes completely, the radius changes completely, everything changes. Yeah. All this is
That's a bounded ratio.
bounded ratio.
Oh yeah,
That's the ratio.
It's a bounded ratio. The whole point, I care now about multiplicative errors.
I see.
I know this is unusual.
Kasra, if we put rho in front of arcade, then it's a projection boundary.
Well, I mean, the issue of what do you mean by closest point projection? This what I wrote here is correct for axis of any pseudo-Anosov and mapping class. This is the theorem with more. Yeah. That's right. With the rho, which depends on the generating set and so on. Yeah, this is always true for everything. Yeah. That's correct. Okay, so let's start. So I pick my 5 functional spheres. I have the usual curves, so I call this one alpha 1. I call this one alpha 2. Note that alpha 2 is joined from alpha 1, so it's not the rotated one, it's just written by 2 clicks. Right? This is alpha 3, this is alpha 4, and this is alpha 5. Right? So my indices are going to be in a Z mod 5, so I can add and subtract in Z mod 5. So intersection of alpha I and alpha I plus 1 is 0, right? So if I write di, that usually means d alpha I, which is the Dane twist, around the curve alpha y. And then I pick my generators to be elements of the form of Si I plus 1 and also Ti. So Si I plus 1 is, I do a di n times, and I do the di plus 1 negative 1 time. So I do a whole bunch of twists around one curve, and I untwist around the adjacent curve just once. And Ti is just the d alpha. I don't know why I named it something else, but it's TNS. Yes?
Fix n.
N, yeah. So what is n? So you can put an n here if you like. And n is an extremely large number, which we chosen later to make it bigger than all the constants that involved in the hypermonicity of Kerr complex or any other theorem we have heard. But the radius will be chosen much bigger than n eventually. So n is very large, but it's a fixed number. So if something depends on n, it's still uniform because it's chosen once. But I can choose n large as I please, right? So I give a extremely, so this Ti is just the Dane twist around the alpha i's and their inverses. They would already generate everything. Yeah, maybe I should call this Ij. want the I minus j to be equal to 1. So you could twist around the previous guy or the next guy, I don't care, right? So you could, if I twist a lot along alpha, then I have to pay a price by twisting around one adjacent guy in the opposite direction. So what is the, so that's the generating set, right? So that's the first of the statements in the generating set. So I need to do some work. Let me just do an example so you see what is this good for. Right? For example, let's say I have a d1 to the power of n to the k. That's a huge, huge database, right? Normally, if you want to write this as product of union of the usual generating sets, it would just be word length n to the k, right? Times some constant which I don't know. So I want to have something which is definitely shorter than n to the k times some constant I don't know, right? So that's why this n is so big. So how do I do that? Using this kind of generators. So first, maybe I do d1 to the, so I do s1 2 to the power of n to the k minus 1. So what does that do? Let's write secretly down here so we can cheat. That's d1 to the power of n to the k, and then d to the power, t to inverse times the power of n to the k minus 1. Right? So it gets them all the big twists, but adds a little bit of a.
So I'm kind of lost here. You're gonna show that the word length is much smaller than n to the k?
That's right.
Okay.
I'm going to write it down explicitly. So first I get up the biggest one, but I add a tiny bit of extra guys. Right? Then I do the second one, n to the k minus 2. So what is that? That does d2 to the power of n to the k minus 1, but subtracts d3 to the power of n to the k minus 2. Right? So every time I get up the big twist, I'm very happy because the word length goes way down, but I have a little bit of extra junk I have to deal with, so I do that. So I just keep doing that. So s3/4 to the power of n to the k minus 3. So I would get eventually sk k plus 1 to the power of n to the 0. And at this point, I have only the last thing I've done. That was dk to the power of n, dk plus 1 inverse, right? So I just need one more element to get at the last two, and that's the tk plus 1. So what have I shown? Is this clear that this product of these elements is that? So I have shown that the word length of b1 to the power of n to the k is less than or equal to let's do n to the k minus 1 plus n to the k minus 2 plus n plus 1 plus another 1, so plus 2. And this number is much less than n to the k. Right? So I have saved money. So this is what I kind of want to show. I want to say this, in fact, is the best way to do it. This is a geodesic. Right? Like the sequence of these words, in fact, is a geodesic connecting identity to this particular huge power of datas. Because other things would take much longer. And this sounds very reasonable. Unfortunately, it's very hard to do it. It's not so easy. So I need a trick to, in fact, get the lower bound for the word length. At this point, I thought this part should be easy, but it actually wasn't. So if anybody has a good solution for that, then you can generalize this to the higher surfaces. But okay, so that's first the generating set. How do I prove lower bounds for word lengths? To do that, I need it would be nice to have a mapping to z, which is kind of a length function, which could tell you that you cannot build things up too quickly. And in this case, there is a length function. So remember that in my case, if I write S05, by this I mean the pure mapping class group. Right? So the punctures are fixed. The punctures are fixed. In particular, there is no half twist in my business. You just do full twist. The good thing about full twist is there are less relations. So your life is a little bit similar. And now I produce a homeomorphism from this object to z, and I do it like that. So So let's say let gamma j. So if I pick any curve in a 5-time punctured sphere, it always divides this to two subsurfaces. One of them has 2 punctures, one of them has 3. Right? So for example, let's pick something like that. And that's 1, 2, 3, 4, 5. I would call this gamma 1, 4. Right? If I write gamma 1, 4 means the part of it which has 2 punctures has punctures number 1 and 4. Okay? So gamma ij is a curve which separates I and j from the other 3. And I send this to either 1 or negative 1. So a Dane twist around this curve. I send to I if I and j are consecutive. And I send to negative 1 otherwise. This is an honest homeomorphism. Somehow I haven't seen this before. Is this known? I mean, Dan is here, Maud is here. Have you guys seen this before? It should be something famous. How, I mean, I don't know. Somehow I've never seen this before. So let me prove that this is a homeomorphism. So if I was using the non-pure mapping class group, I would be in trouble.
Yeah, it's some kind of winding number, isn't it?
Yeah, but I'm kind of choosing the orientation of these functions 1, 2, 3, 4, 5. So it's very
Well, you have,
natural.
you have a winding number around each puncture, right?
No, but I have to do negative because I have lantern relation. So the y number doesn't work by itself. I cannot just add up twists.
They're all positive twists.
They're all positive twists. All right, let's check that this is a homeomorphism. So what are the relations? So according to a presentation of the mapping class group given to you by Feng Luo, mapping class group is generated by all Dane twists. Right? So what does Feng say? It says you can choose a presentation of mapping class group.
So are you looking at the action on the curve, and then you look which ones are separated from which one? How do you?
No, I just randomly chose ordering of the punctures, 1, 2, 3, 4, 5. Then I pick a curve. If it's separating 2 adjacent punctures from the other ones, I send a Dane twist around this to
You
1.
pick a curve, not an element of mapping class.
I pick a curve,
So that's a map from
and then,
curve class?
no. I pick a curve, which has a property, and I send a Dane twist around that to 1 or negative 1.
Oh, it's about things.
That's right. And then since these guys generate, I say that this is a homeomorphism of the whole method.
How does the homeomorphism depend on your random order, your ordering?
Well, if I pick the 1, 2, 3, 4 differently, then different guys will go to 1 or negative 1. Being adjacent is
So
not
it
a...
changes. It changes. You have a family of.
I'm a family, yeah, that's right. But yeah, that's right. But I pick this one. That's right. So, so presentation of Monkas group. What is the presentation? So you have all the alphas, if you like, which is so the infinite presentation is the all things, and then so what he says is like all relations can be put into small subsurfaces, like so either rank 1 or rank 2 subsurfaces, and there's a whole list of these guys. But in the case of pure rapid task group of 5-puncture torus, there are basically 2 different relations. There's the lantern relation, and then there is the other relation, which is the Dane twist around phi of alpha is phi Dane twist around alpha phi inverse. Right? So this is the presentation of the mapping class group. So if I want to say this is a homeomorphism, I have to check these relations. This one is clear because whatever value this function has, this has the inverse of it. And if I move alpha by homeomorphism, its type doesn't change. It still separates the same 2 from the same 3. So this is easy. Maybe I should call this L. So I really have to just check the lantern relation.
Does this homomorphism factor through a product of forgetting modes?
Not that I know of. You tell me, I don't know. It's just, it is what it is. Yeah. If somebody tells me something about it, I'll be very happy to know. So, yeah, let's check the lantern relation. So 1, 2, 3, 4, 5. What are the possibilities? The lateral relation is something like this. B alpha, so B gamma ij, B gamma jk, B gamma ki is equal to B gamma lm, right? So just name the 5 vertices I, j, k, l, and m. So it has to be involving 3 of them, going pairwise around them, and then you get the boundary, which is the other side. So usually, the lateral relation should be the product of 3 Dane twists equals the product of 4 Dane twists. Here, 3 of them will be punctured, so they don't do anything. So what you would get is the other guy. Let me draw this by arcs. So if this is 3 of your arcs, this is the other arc. And in fact, there are 2 cases only. Either ij and jk are both non-adjacent, or 2 of them are adjacent. So if 2 of them are non-adjacent, the other one has to be adjacent, and the boundary becomes non-adjacent. And if 2 of them are adjacent, the third one has to be non-adjacent, and the boundary is also adjacent. So in this case, you have -1 plus -1 plus +1 equals to -1. And here you have 1 plus 1 minus 1 is equal to 1. So that's the proof. Okay, so what is the consequence of this? If you have a length function, you get lower bounds on word lengths. What do my generators do? I have 2 kinds of generators. One of them which does n to something and -1, so does n minus, changes the homomorphism by n minus 1, and the other one that changes it by 1, right? So the lemma is that if I pick L of some phi, and it turns out that this is like A n minus 1 plus B, and B is small, let's say B is less than n minus 1 over 2. So depending on the value of your homomorphism, if you're written like that, the most efficient way to write this as a sum of n minus 1s and 1s is to use n minus 1s and b 1s. So then the word length of phi is bigger than or equal to a plus b. So should I prove this? Why is that? Because if I write my phi as a product of, so here I read a quick proof of this. If I write phi as a product of u1 to um, then if I apply L of phi, that's L of u1 to plus L of um, and each L of ui is either 1 or n minus 1. So I have written this number as sum of a bunch of n minus 1s and 1s, and the best way to do that, if b is small, is to use as many n minus 1s as we can. So I translate my issues, I have Lacan class group into Z. So in particular, in the example that I have, that means, so L of this d1 to the power of nk is equal to what? Well, is equal to n to the k, because this is just 1. And I can write this as n minus 1 times n to the k plus n to the n minus 1 all the way plus n plus 1 and plus 1. So this is my factor. The remainder here is 1, which means the word length of d1 n to the k is bigger than or equal to n plus n to the k minus 1 plus n plus 2. Right? And which is exactly the number of elements I used. So I actually found the word length of some large element in the mapping class group with respect to some weird, crazy generating set. So like
It's an n to the k.
n to the k.
First term.
minus 1, and k minus 1. Okay, so everybody happy with this so
What's
far?
U1 in the,
U?
so did you use the notation U1?
Yeah, U1 is, for example, in here is S12. And I use S12 a whole bunch of times. Then I use S23 a whole bunch of times. Yeah, I mean, basically,
What's L of U1 is equal to N minus 1 that we run?
L,
No, the L of U1 is equal to N minus 1?
L of
Yeah, what?
U1 is either, so these UIs are the generating sets, right? And my generating sets are things of the
Okay.
form
Yeah.
do n positives, 1
I didn't
negative.
see the 1.
That's right. Or 1, yes. It's either 1 or n minus 1. Okay, so very good. So we have a generating set. Let's pick a, what do we need? We need a pseudo-Anosov element, we need WKs, and we need RKs. We don't have so much time. So let's do that. So the pseudo-Anosov, that's the easy one. So I picked the pseudo-Anosov to be the product of 5 day integers that I have. Those to be symmetric. So D5, D4, D3, D2, D1. You can, in your spare time, you can check if this is pseudo-Anosov. You can actually write a nice train track that is preserved under this. It's not so hard. Yeah, so it's a good pseudo-Anosov. Okay, so very good. And I have my quasi-access, G of phi, which I pick my mu0. The mu0 I'm not going to use, but if you want to have a marking that curves alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, works as a nice marking. This is a filling set of curves, right? So it has some distance to the axis, but since these are fixed once and for all, I don't really care. And this phi, yeah. So let me just write like that. This is identity, this is phi. So the orbit of identity on the phi fellow travels the axis, and for all practical purposes, I'm just going to work with these guys instead of with the axis. So axis is somewhere, I don't really care about. Okay, I need a word WK that I can somehow compute is distance to this axis. That's what I want now, right? And I want the word to be somehow a large power of twist. So in the curve complex, it projects to identity. But I want it to, the closest point projection of that to the axis to be somewhere way over here. So that is my goal I want. To cook up a big power of a twist, which in the curve complex looks like it's here. But the mapping class group thinks it's like it looks on top of here. Right? So I do that.
Wait, before you erase that, in your,
I'm not going to erase it.
in your theorem,
I'm going to keep that for a while.
is the projection the closest point projection?
Closest projection.
So it's not your original projection projection?
That's right. It's actually the closest projection. Yeah, don't know. I'll keep that up. Okay, so we did one example of some crazy word that you can find the word length. So I'm going to write even a crazier word that you can find the word length of. And the crazy word is you pick D1 to the power of nk plus nk minus 1 plus nk minus 2 plus n plus 1. And multiply this. This is a real well writing it, but bear with me. D1 inverse, D2 inverse, D3 inverse, all the way to K inverse. Again, note that these numbers are mod 5, so K is a really, really large number. Right? So you're picking K to be much bigger than N here. So I'm saying that you can compute the word length of these guys. So why is that? In fact, so let me call this word, I'm going to call this is my WK. And this one is phi to the power of K over 5 inverse. Right? So the word length of this is the distance in the mapping class group in this generating set between wk and phi to the k over phi. So I want to say this wk is on top of phi over k over phi almost. Right? So this is how this is cooked up to be. Yeah, basically I can write this explicitly as product of Sij's. And you could tell me how I do it. See, there's a 1 here which cancels with that. And if I do the S12 enough, I divide this by n. And there's extra 1 left, which is a D2. That cancels with that. And what is left, I can divide by n, and so on. Right? So just trust me that this word is written, can be written as the product of a bunch of S12 to the power of that number. Yeah, maybe I write explicitly instead of naming it. It would be n to the k minus 1 plus n to the k minus 2 plus n plus 1. Then I have to do S23, n to the power of k minus 2 all the way to 1. Then S34, n to the power of k minus 3 all the way to 1, and so on. Right? So there's a nice word like that, which uses only these big powers to write this down. So that gives me upper bound, and the L gives me the lower bound. So basically, the value of L here divided by n is the correct number for this distance, and that number is n to the k plus n to the k minus 1 plus 1 minus, I think I need k plus 1 of this divided by n minus 1. So whatever this number is. Okay? So I can compute the word length of this element on the nose. Because I can write it down and I can find it out. So I compute the distance from here to here exactly. So this distance I call dk.
Oh, man. Dangerous bucket.
What should I call it? Rk is a distance to the axis. You might be happy at the moment, but you don't know that this, even though this is a super efficient way to go to the place I cooked up in the axis, still you don't know that there might be somebody else which is closer. So that's going to be my Rk.
Delta.
Delta. Thank you. Excellent, excellent. Delta. Delta. Oh, 1 more minute. Oh, I'm finishing by 10 before. Okay, I'll just wave my hand then. I mean, I have told you everything you need to know. From now on, you should be able to finish it up. I thought I'd go to the actual hour. So what happens? So first of all, since you picked this so precisely, you're hoping that this is the closest point projection. But you don't know that. But if you look at your homomorphism, you see that if I go this way, the value of homomorphism goes up. So the closest homomorphism cannot be this way. It has to be the other way. And you know that if I go the other way, every n step I make, the value of homomorphism goes down by 1. So you prove that you cannot go so far this step. In fact, you use a version of this projection of the row to prove that the projection of this whole thing over here is logarithmic. So what you can do here is logarithmic. So the Rk turns out to be dk minus k times log n over n.
You mean delta?
Delta k. Delta. Right? So you don't lose very much at all. So you find that the closest projection to the axis is somewhere on the right and is not so far away. And then you pick some other word, which means so what I used to write this to come to the axis, what I used was S12, S23, S34, and so on. But I could do S12, S21, S12, S21, and they all would cancel each other out. And instead of coming over here, I would come somewhere over here. So with the same distance Rk, I can come to some point Uk, which ends up to be at a k over n around the identity. So you can do that explicitly. So the close projection from here is somewhere over there. There's a point distance r whose contribution is somewhere over here. The distance between these two guys turns out to be bigger than k over 6. And k is log of r and your. Okay, thank you very much.
still some other projection which would have a strong contractive property? Or is this some Lipschitz projection that isn't close to point? So it's still.
No, the curve complex projection. Oh, I see. Yeah, that's a good question. No, it's possible. Yeah, definitely. From this, it's still possible. But this is kind of the first time that you have a ball of radius something, and the projection is logarithmically big. And I should say that logarithmically big is the best you can do. You can push the original argument. It is not bounded. You can prove logarithmic. But actually, logarithmic is possible. Yeah.
Okay, well, there's going to be a coffee break now, and the next talk is at 11:15. Let's thank Kasra again.